Today, we're going on a quest. We're talking about one of the most famous charts in all of science, the periodic table. And trust me, it is so much more than just a poster you see in a chemistry classroom. It's really the story of a huge, centuries-long hunt to find some kind of order in the very building blocks of our universe.
So, let's set the scene. I want you to imagine you're a chemist back in the 19th century. New elements are being discovered left and right. I mean, it's super exciting, right? But it is also a complete and utter mess. How on earth do you even begin to make sense of it all? That was the big puzzle of the time.
You had dozens and dozens of these elements, each with its own unique personality, its own properties. Chemistry just felt like this random collection of facts. Scientists desperately needed a system, some kind of map, to navigate this growing world of matter. Without one, they were basically just lost in a chemical wilderness.
But, even in all that chaos, a few billion minds started to spot the first clues. They began to suspect that maybe the elements weren't random at all. Maybe they were part of some grand, hidden pattern. So let's look at the very first real attempts to crack the code. Okay, so the first real breakthrough came from a German chemist, Johann Wolfgang Dobereiner. Back in 1829, he noticed something cool. He saw that he could group certain elements into little sets of 3, which he called triads. And these weren't just any old groups. The elements in each triad had remarkably similar chemical properties.
And here's the part that's so fascinating. The math actually worked. Check out the triad of lithium, sodium, and potassium. If you take the atomic weight of the lightest one, lithium, and the heaviest, potassium, and just average them, you get 23.0. That's the exact atomic weight of sodium, the element right in the middle. This was the very first big hint, that atomic weight was probably the key to this whole puzzle.
All right, let's fast forward to our next clue finder, an English chemist named John Newlands. In 1865, he took a much more ambitious swing at it. He arranged all the known elements in order of increasing atomic weight, and he saw something that must have been mind-blowing. Their properties seemed to repeat in a pattern of 8.
This quote really gets you inside his head. Newlands actually compared this repeating chemical pattern to a musical scale, where the 8th note is basically a repeat of the first one, just an octave higher. He even called it the law of octaves. It's a really beautiful, intuitive idea, isn't it? But of course, these early models weren't perfect, not by a long shot. For one, Dobereiner couldn't find triads for all the elements, and Newland's octaves kind of fell apart when you looked closely. It forced elements with totally different properties into the same groups. And maybe the biggest problem, it left no room for elements that hadn't even been discovered yet. So yeah, they were vital first steps, but the masterpiece was still to come.
And that brings us to the absolute titan of this story, Dmitri Mendeleev. This is the guy who took all the existing clues, threw in his own brilliant insights, and created the first truly powerful and predictive periodic table.
Here's the man himself. You see, Mendeleev wasn't just trying to organize elements. He was searching for the fundamental law that governed all of them. The story goes that he worked on it relentlessly, playing a sort of chemical solitaire with cards he'd made for each element, just shuffling and arranging them until the pattern finally clicked into place.
So what made his table such a game changer? Well, like the others, he started by arranging elements by atomic weight. But, and this is key, he prioritized their chemical properties above everything else. If an element didn't seem to fit, he wasn't afraid to move it. And here's the most brilliant part. He left gaps. This wasn't him saying, I don't know. It was a bold prediction that new elements would be discovered to fill those spaces. He even predicted their properties with stunning accuracy, which pretty much turned chemistry into a predictive science overnight.
And here it is. Now this might look a little different from the table we're all used to, but the core structure is all there. You can see the vertical groups of similar elements and the horizontal rows. And see those empty spaces? Those weren't mistakes, they were predictions. And that level of confidence is really what set Mendeleev apart from everyone else.
But, even this masterpiece had a flaw, a nagging little problem. To keep elements with similar properties together, Mendeleev sometimes had to break his own primary rule of increasing atomic weight. Just look at tellurium and iodine. Tellurium is actually heavier, but he placed it before the lighter iodine just so it would fit in with its chemical family. He knew in his gut it was the right move, but he couldn't explain why. This little inconsistency, these anomalous pairs, well, they suggested that atomic weight, while really close, wasn't the final answer. There had to be some deeper, more fundamental property at play. The puzzle was just missing one last piece.
And that final piece clicked into place in 1913, thanks to a young physicist named Henry Moseley. He discovered the true organizing principle wasn't weight at all. No, it was the atomic number, which is simply the number of protons in an atom's nucleus. This discovery completely redefined the periodic law itself. Properties didn't repeat based on mass. They repeated based on proton count.
And just like that, boom, the problem was solved. Moseley's discovery instantly fixed Mendeleev's little anomaly. See, tellurium has 52 protons, and iodine has 53. So of course tellurium comes first. The order was right all along, they had just been measuring the wrong thing. The great chemical puzzle was finally complete. Okay, so with the puzzle solved and the map finally perfected, let's take a quick tour of the modern periodic table and just see how much amazing information is packed into it.
And here it is, in all its glory, the beautiful result of that entire quest for order. The modern table is organized into 18 vertical columns, which we call groups, and 7 horizontal rows, called periods. Every single element has its own unique address based on its atomic structure. It's just elegant.
Now, the real key to reading this map lies in the columns, those groups. It's best to think of them as chemical families. Elements in the same group behave in very similar ways, and that's because they have the same number of electrons in their outer shell. For instance, everything in group 1, the alkali metals, they all react explosively with water, and everything over in group 18, the noble gases, is famously unreactive and stable. It's all in the family.
The table's geography also tells a story. You see this little staircase line running down the right side? It's a really simple divider. To the left, you've got all the metals, shiny, good conductors. To the right, you have the nonmetals. And the elements that sit right on that border, those are the metalloids, which have properties of both, and they are absolutely crucial for making things like semiconductors. It's an incredibly neat visual guide.
But this is where the table's real power comes into play. It's predictive trends. So many properties change in really predictable ways as you move across a row or down a column. For example, look at atomic radius. As you go down a group, atoms get bigger. That makes sense, right? You're adding more shells. But as you move from left to right across a period, they actually get smaller. Why? Because the nucleus is getting stronger and it pulls the electrons in tighter. Once you understand these trends, you can predict how an element will behave without ever even touching it.
So the big takeaway here is this. The periodic table is so much more than a list. It is a predictive tool of immense power. An element's address on this grid reveals its size, its reactivity, what kind of bonds it likes to form. Basically, its entire chemical personality is right there in one little box. So we went from a total jumble of disconnected facts to this perfect, elegant map of matter. But here's a final thought for you. We are still creating new, synthetic, super heavy elements in labs. As we push further and further into this unknown territory at the bottom of the chart, will Mendeleev's map continue to hold true? Or are there new patterns and maybe even new laws of physics still waiting out there to be discovered?